Hi guys, welcome to the final demo video of HandsOnTech Silicon Valley for the Build a CubeSat challenge. So this is a picture of our team. And flooding is a commonly occurring natural disaster that happens every year all over the world, and our goal of this mission is to design an AI model that constantly takes picture to detect flooding and prevent losses of economy and human lives. This is our system overview where we have a satellite that's observing the ground and taking pictures so we can detect flooding and compare the pictures of flooding and normal. And for one satellite obviously can't do the entire job, so we need hundreds of satellites to actually cover the entire Earth. Now I'm gonna hand it over to Brady to dive deeper into the ConOps system and the system of our CubeSat.
So this is our ConOps diagram, or our concept of operations. It's a basic overview of what really goes on when we run our system overall. So at the start we turn on our system, and then we start testing for pre-launch, and if it doesn't pre-launch, then we reboot it and we try to do it again. If pre-launch is successful, we go to orbit insertion where we try to enter orbit. And if that's successful, we move on to the, our functions. If it doesn't work, this should go to failure. We made a mistake when we made this diagram. It goes back to the rebooting system, which doesn't really work, but just imagine this goes to failure. In the case that either the error contingency or our entering orbit is successful, we enter our functioning stage where we just kind of run our subsystems and we do our testing. So the subsystems that we are going to deploy are like camera, communications, power, ADCs, all of that stuff. And you can see it's over there. And once everything's done, we end our system. Now we can talk about our system design in space. So we have two main parts, which is hardware and software. With our hardware, of course, we have our CubeSat, which is the whole thing. In that, we have the Raspberry Pi, solar panels, batteries, NPU, reaction control systems, camera, and communications. All of these different hardware systems are all used to help, contribute to moving the CubeSat, taking our images, transferring the images to the ground station at MIT, and so on. And then with those hardware, we have our own software that we've implemented. So we have a central controller. This helps us move the CubeSat across our rail to simulate that the CubeSat is in orbit. We have movement to help with movement. We have imaging. This will help us that whenever we move along the orbit, we can take images of our testing environment and simulate, flooding or not flooding. And then we have communications to help us send the images to our ground station whenever we need to. Some of these other software things that we implemented are stuff like shoreline detection and flood detection. For example, the shoreline detection part could be more known as ocean detection. So in the case that our imaging takes an image of just ocean, we already know that that's not going to have flooding, so we have to send that, and we save time on our communication side. And flood detection helps us, detect floods as stated by our missions.
So this is our CubeSat, and this is our software flowchart. I'm going to be discussing how our software works and how it integrates with everything in the subsystems. So our journey starts with our CubeSat moving to a specific spot on planet Earth, and we're going to be taking a timestamp of that location, and then running our ocean detection model. So why we need to do this is because we don't want to photograph places that are just ocean, right? Because that's kind of useless. That is not the point of our CubeSats. So if it is not the ocean, we're going to be taking a picture, and then we can save the picture in our image management database along with the timestamp that we took. So with this image, we're going to be going into our image processing subsystem. So we are going to be splitting our image into a couple sections. Why? This is because our shoreline recognition and flooding detection models do take up a lot of CPU usage, and it's kind of slow to be running it on the entire model. I mean the entire image. So we split it up, and then we're going to be putting it into our shoreline detection so that we know which part of which sections are water and which sections are land, based on each of these sections that we split off the original image. So we're going to be also doing our change detection in order to detect where flooding happens. So the way we do this is we store the image, right? And then the next time we come into this location, we can compare the two images, and then we can see the difference between the two images, and that's where the flooding is going to be occurring. So then when we fly over a ground station, we can transfer the data to the ground station and tell them where the flooding happens.
So this is our testing environment. So for our testing environment, we created a map that simulates the Western Hemisphere, which we have North America and South America. To simulate flooding, we used colored papers, and then using a railway and a robotic arm, we simulate the CubeSat track on Earth, and then the railway is to simulate the CubeSat in orbit. Yeah, so this is our flooding detection system. So as you can see, we implemented the colored papers here. And then through this, we take an image and process it through, in which we break that image down into 1,000 different small images to gather better accuracy on the data we have. And then given that data, we send it through our model to detect, whether it's flooding or not, and then we return a binary of whether it's not flooding or if it's flooding.
Hi, so this is our CubeSat, and we use a cable car-like system that runs across the ceiling to control the CubeSat's movement and simulate the CubeSat's movement in orbit. And so we use the motor spool control system to simulate the CubeSat's movement in the latitude direction, and we used a controller arm to help position the CubeSat in the longitude direction. And so this is our testing environment. We use a tennis table, because it's blue to simulate the ocean. And we cut out brown paper to represent the Western Hemisphere, and we used colored paper to help simulate the before and after of flooding. And this is our ground station. So right now the CubeSat is moving in the latitude direction. So it's also moving in the longitude direction. The CubeSat arm is moving to help position it to take photos.
Now I'm sending a file from our Raspberry Pi on the CubeSat to my own home computer, which we are simulating as the ground station. So here we can see CubeSat. The 37 is the IP address that we're using for the Pi, and then here's the file name, here's the status, and here's the time remaining. Okay, and I finished sending. So now I can pull up the image, Pi at here, and then this is what it looks like from our Raspberry Pi.
So here are some problems that we encountered. So one issue we ran into was that it was difficult to take clear images when the lights were dim. So this may mean that when there's certain weather, really cloudy weather, it might be difficult to get accurate photos. Also, the controller arm didn't have enough power to raise the CubeSat in really high degrees. Another issue was that using a cable for the cable car system was sort of inaccurate, and it couldn't move the CubeSat to a specific distance. And also the machine learning model consumed too much CPU. So some potential enhancements that we could do is find a way to account for tides for shoreline detection, because we want to be able to differentiate between high tides and flooding. We also want stronger motors for the controller arm, and we want to use a chain-based cable car system so it's more accurate when moving the CubeSat. We also want to try adding a auto charging subsystem, because right now the CubeSat can only charge when it goes to like the charging station. So we want to be able to like have it charge when it's also not there. And then we also want to optimize the machine learning algorithm so it won't consume as much CPU. So here are some things that we learned. So we learned how to apply like information that we learned from the course to like a real life project. We also learned how to create and design a CubeSat system and like make it work and like help us like achieve our like mission goals. We also learned like better teamwork skills like collaboration and like communication. We also learned a lot more about like using CubeSat and like the different hardware and software components. Okay, so thank you.